LODs, when cheating on players actually improves performance. Hello and welcome to episode number 6 of the Unity Performance Task Force. I'm your host Ruben from TheGameDev.Guru, and as usual I'll kick off with a question for you. Have you ever watched a beautiful 3D model suddenly pop into existence right in front of your camera, or worse, vanish into thin air as you back away? That jarring moment when your brain screams, something's wrong here, but you can't quite put your finger on it? That's LOD popping, and if you're shipping a 3D game, you've either dealt with it or you're about to. Today we're talking about level of detail systems in Unity. Why you need them, how to set them up without making things worse, and 3 sneaky workflows that most developers don't know about. So here's the fundamental problem. In any 3D game where players can move around, your geometry ends up in 2 very different situations. Sometimes it's right in your face, taking up half the screen, demanding every triangle and vertex you can throw at it. Other times it's a tiny speck in the distance, barely occupying 10 pixels. And here's the thing. Rendering a million vertices just to display 10 pixels on screen is not just wasteful, it's actively destructive. Your GPU chokes, your frame time spikes, and worst of all, you get this ugly shimmering effect called geometric aliasing. That's when you have so much geometric detail compressed into so few pixels that the image starts to shake and flicker as you move. No amount of anti-aliasing will save you there. So the solution is simple in concept. Swap to simpler meshes when objects are far away. That's level of detail, or LOD for short. Now, most developers know LODs exist. What they don't always know is how much performance you're leaving on the table by not using them correctly, or how badly you can hurt performance by setting them up wrong. Let's start with what LODs actually give you. First, memory bandwidth. The fewer vertices you push from RAM to VRAM to GPU cache, the less you clog that pipe. And memory bandwidth is the silent killer in game performance. I saw a tweet from a graphics expert recently. Memory efficiency only improves about 5% per year. Compare that to the Oculus Quest 2 jumping from 72 to 120 FPS in a single software update. You can't rely on hardware to save you here. Second, vertex shading cost. Fewer vertices means your vertex shader runs fewer times. Modern GPUs share shader units between vertex and fragment work, so even if you're fragment bound, reducing vertex load can free up resources. Third, and this surprises people, you can reduce draw calls. Not automatically, you have to be smart about it, but if you swap expensive multi-material meshes for single material versions at distance, you can cut draw calls in half or more. That helps your CPU as much as your GPU. And fourth, like I mentioned, LODs reduce geometric aliasing. A simpler mesh at distance actually looks better and more stable than a hyper-detailed one because the pixel-to-vertex ratio is healthier. So how do you actually use LODs in Unity? The basics are dead simple. Let's say you have 2 versions of a mesh. LOD0 is your high-poly hero model, LOD1 is a simplified version with maybe half the triangle count. You create an empty parent GameDev.Guru, add an LOD group component, and drag your meshes into the LOD0 and LOD1 slots. Done. Unity shows you a little percentage bar. That bar represents screen height, how much of the screen this object occupies. You drag the transition point to control when the swap happens. If you set the transition at 50%, Unity uses LOD0 when the object fills more than half the screen height, and LOD1 below that. Now here's where people mess up. If you set those transitions too aggressively, players see the swap. That's LOD popping. The model suddenly changes and the illusion breaks. In a AAA game, that gets you mocked on Twitter. In your game, it just pulls players out of the experience. There are 2 main ways to hide LOD popping. The first is careful tuning. Adjust those transition distances so the swap happens when the visual difference is minimal. The second is dithering. Dithering is a crossfade technique where Unity makes some pixels transparent and some opaque during the transition. The ratio changes over the fade width, so instead of a hard snap, you get a gradual blend. It looks way smoother. To enable dithering in Unity, you need to do two things. First, download the built-in shader source from the Unity archive. Find the standard shader, copy it into your project, and open it up. There's a comment that says uncomment the following line to enable dithering LOD crossfades. Uncomment that pragma. Save it as a new shader. I usually call mine standard epic just to keep track. Second, set your materials to use that shader. Then in the LOD group, change the fade mode from none to crossfade and set the transition width. Now when the LOD swaps, you get that nice dithered blend instead of a hard pop. Is dithering expensive? Yes. It discards pixels, which disables early Z optimizations on the GPU, but it's often cheaper than the visual cost of popping, and on mobile it tends to perform better than full transparency. As always, measure in your specific project. Now let's talk about 3 advanced workflows that most people miss. Workflow 1. Common renderers. Let's say you have a door with 2 materials, a solid wooden panel and an expensive transparent glass insert. When that door is far away, do you really need to render glass with refraction and all that overhead? Probably not. So create a second LOD level where you remove the glass material entirely, or replace it with a cheap opaque approximation. Same mesh, 1 material instead of 2. You just halve the draw calls for every door in your scene. Multiply that by 100 doors and you're saving real frame time. This works for anything expensive: animated materials, emissive materials, multipass transparency. At distance, swap them out for static, opaque, single material versions. Your players won't notice and your frame budget will thank you. Workflow 2. The poor man's impostor. This one's a little hacky, but I'm a big fan of hacks that work. Let's say you have a complex mesh with a complex shader, standard shading, ambient occlusion, the whole 9 yards. At extreme distance, you could replace that entire thing with a single quad and a screenshot. Here's how. Position your camera to get a good angle on the object. Take a screenshot using something like ShareX. Import that image as a texture. Create a quad, slap a super cheap unlit shader on it with that texture, and boom! From a distance, it looks almost identical, but instead of 1,000 triangles and an expensive shader, you're rendering 4 triangles and a texture sample. This is borderline absurd, and you wouldn't use it for hero assets, but for background props or distant decorations, it's a lifesaver. And if you're prototyping performance optimizations and need a quick test to see if vertex count is your bottleneck, this trick gives you an instant answer. Workflow 3. Common renderers for partial LODs. You don't have to swap the entire object. Let's say you have a gun model with a high poly barrel and a simple stock. You can assign the barrel to different LOD levels, but keep the same stock renderer in both LOD 0 and LOD 1 by dragging it into both slots. Unity will render the high poly barrel up close, swap to the low poly barrel at distance, but always use the same stock mesh. That saves you from duplicating geometry unnecessarily and keeps your memory footprint tighter. Alright, so when should you actually use LODs? Use them when you're GPU bound by vertex shading or when you have too many draw calls and can reduce them by swapping materials. Use them when you're seeing geometric aliasing on distant objects. Use them in any game where objects move toward and away from the camera, which is basically every 3D game. Avoid LODs when you don't need them. If your game is a fixed camera puzzle game where nothing moves, LODs are overkill. If you're CPU bound by script execution and the GPU is idle, LODs won't help. And if you don't have time to generate quality LOD meshes, don't fake it. Bad LODs that pop constantly are worse than no LODs at all. So how do you generate LODs? Option 1. Manual. If you have the budget, get an artist to create them in Blender using the decimate modifier or by hand. You'll get the best results, but it's slow and expensive. Option 2. Automated tools. I'm a big fan of Simplygon for this. It's free for certain use cases and it lets you import a mesh, tweak a few sliders, and export simplified versions. You spend 20% of the time and get 80% of the result. Even if you don't ship with these meshes, they're perfect for prototyping. You can test whether adding an LOD level would help performance before asking an artist to spend a week on it. Option 3. The poor man's quad trick I just described. Not suitable for everything, but shockingly effective when it works. Now let's talk about the traps. First, occlusion culling. Unity uses the LOD0 mesh to calculate occlusion. If your LOD1 is dramatically different in shape, like if you replace a solid wall with a thin plane, occlusion culling will think the object is blocking more than it actually is. That can cause visible objects to disappear incorrectly. Keep your LOD shapes consistent. Second, draw call inflation. If you have too many LOD levels and they're all visible at the same time because you have 100 objects at varying distances, you can actually increase draw calls instead of reducing them, especially if you're relying on GPU instancing. Unity can only batch identical meshes, so if you have LOD0, LOD1, and LOD2 all on screen, that's 3 batches instead of 1. The sweet spot is usually 2 or 3 LOD levels max. More than that, and you're fighting diminishing returns. Third, dithering and transparency both have costs. Dithering disables early Z, which can hurt fill rate. Transparency can cause overdraw and requires sorting. Test both in your project and see which performs better. There's no universal answer. And finally, remember that LODs load all mesh data into memory at startup. If you have 5 LOD levels per object, you're storing 5 meshes in RAM. That's a trade-off. You're saving GPU time at the cost of memory. Make sure it's worth it. 2 last tips before we wrap up. Unity has quality settings for LODs. You can set LOD bias to shift all transitions closer or farther. If you're porting to a weaker platform, you can set max LOD level to skip the highest detail meshes entirely. That's a quick way to optimize without rebuilding content. And you can use those settings for diagnostics. If you set max LOD level to 1 and your frame rate doubles, you know you're vertex bound. That's a huge clue for where to focus your optimization effort. Alright, let's recap. 1. LODs reduce memory bandwidth, vertex shading cost, and geometric aliasing. Used correctly, they can also reduce draw calls. 2. Set up LODs by creating an LOD group, assigning mesh renderers to LOD levels, and tuning the transition distances to avoid popping. 3. Use dithering or transparency crossfades to smooth transitions. Test both because cost varies by platform. 4. Get creative with LODs. Swap materials, not just meshes. Use common renderers to avoid duplication. Replace distant objects with quads and textures if it makes sense. 5. Avoid LODs when they don't fit your game or when they inflate memory or draw calls unnecessarily. Always measure. This is the exact workflow we use at TheGameDev.Guru when studios need fast wins on vertex-bound projects. LODs are low-hanging fruit if you're smart about it. If you want to dive deeper into vertex optimization, memory bandwidth, or profiling GPU bottlenecks, you can access in-depth lessons in the Unity Performance Task Force program at www.performancetaskforce.com. And if Unity Consulting is what you are after, book a free discovery call at http://consulting.thegamedev.guru. Till next time.